So, I think I've got to tell you one sad thing. The next talk will be the last session of RubyKaigi this year, which will be performed by Mr. Aman Gupta, who's also known as TMM1 on the internet. It's coming. He's been a Ruby core community since 2 or 3 years ago, I guess. I don't remember exactly, but
2 years.
2 years ago. And since then, he's made lots of significant contributions, such as performance improvements. He's, I believe, working on the most difficult part of the Ruby implementation, such as Ruby VM. So, here comes the final keynote speaker, Aman Gupta.
Thank you. Konnichiwa, RubyKaigi. I want to start out by saying I have a lot of stuff to cover, and I'm going to try to go slowly so you guys can understand. But I've posted my slides up on this bit.ly link, bit.ly Ruby 2.1 in production, and my presenter notes are there. So if it's easier for you to read the English, feel free to grab that. Before I get started, I want to thank all the RubyKaigi organizers for inviting me to keynote. It's truly an honor. I have to say I'm a little nervous because the last time I gave the final talk at a conference was at Mountain West, and somebody grabbed this photo. Matsi kind of fell asleep, so hopefully that's not the case today. So a little bit about me. My name is Aman Gupta. I go by TMM1. I am the VP of Technical Infrastructure at GitHub. Some of you might have heard of that company. We run a large Rails application. It's the largest code host in the world right now, with over 15 million repositories, over almost 100 terabytes of Git data on our servers. It's a pretty large app, and we serve a lot of traffic. Here are some numbers. We do about 3,000 requests per second, and the average response time is about 85 milliseconds. It's a completely Ruby app. And we actually measure our response times not in averages, but in percentiles. So this is what our we call this our application performance dashboard, and you can see we're measuring on here the 98th and 99th percentile. So 98% of requests to GitHub.com are completed in 312 seconds. And one of the things you'll notice on here is we break down our response times in a lot of different categories. Like I mentioned, we don't like to use average response time because the response time is very varied depending on the type of request. So AJAX requests, for instance, or API requests tend to be much faster than somebody in a browser. And so we break it down and get a much better sense of where our performance lies. So today I basically want to tell the story of how I upgraded the GitHub.com Rails app from Ruby 1.8.7 P72 to 2.1.2, which runs today. Before I get to that, though, I just want to talk a little bit about myself. So I actually discovered Ruby way back in 2002 in high school. I was a young developer just learning about web development, getting super into PHP. Some friends and I created this online game that got a little popular. And I was a huge PHP fanatic back then. I used PHP for everything. I would write shell scripts in PHP. I actually wrote like 3D games in PHP. Apparently you can like use OpenGL bindings with PHP. PHP everything. But Ruby was very interesting to me. I found this programming Ruby guide one night just randomly, and the simplicity of the object model really appealed to me. However, there was not really a way to do web development, so I lost interest and I went back to PHP. A few years later in college, I started hearing about Rails. And I bought the Rails book, like everybody suggested. I read it a few times. And I was really interested at that time in real-time push to the browser. And so I was like, this framework looks great. Let me open it up and try to add real-time support. And no, that didn't work. it was way too confusing. I couldn't really follow all the meta programming. There was, especially back then, this was, I think, right about Rails 1.0. It was very crazy code base. And so I, again, gave up and sort of swore off Rails. But I did find some alternative web frameworks and database toolkits. So I got heavily involved in the Ramaz web framework and the SQL database toolkit. Started contributing patches to that. I also got super into Ruby Event Machine, which was, again, part of the whole real-time push, and eventually took over as maintainer of this project. And so a few years later, fast forward, I moved to San Francisco. This was in 2008. This was a big change for me. I moved across the country. I grew up on the East Coast, so all the way to the West Coast, brand new city. But it was actually a very exciting time to be in San Francisco as well. At that time, I don't know how many of you knew Josh Susser, but he used to host this secret underground Ruby meetup called ICANN Has Ruby. The problem with all the mainstream meetups were they were very recruiter-focused. And so we started this sort of secret one where everyone would get together. And it would happen at companies like Twitter, Pivotal, companies that were just up and coming. A lot of people were using Rails. And so it was a great way to meet a lot of Ruby developers in the area. And this is where I actually first met Mojumbo and Defunct. And they were working on something called github.com on the side, just in their spare time. Eventually, actually, the ICHR meetups, they actually didn't last very long. They sort of died out. And it's a funny story, actually. So in the beginning, we would all go to ICHR because that was the way you would find out what is the new gem someone's working on, what is the latest Rails plugin. And you would go and hear those people talk about the things that they were doing. However, as soon as GitHub started taking off, what happened was by the time we got to ICHR every week, we already knew what everyone was doing because we saw their activity on GitHub. And so the ICHR started dying out. But what took over in San Francisco was the GitHub drink-ups. So the GitHub founders at that point started doing bi-weekly drink-ups. So it was always either drink-up week or the next week was drink-up week. And we would actually all count down the number of days because it was a great way to like catch up with people. And especially for me, having just moved to the city, a brand new city, it was a great excuse to go out, explore different parts of the city. It would be held at a different bar every other week. And so we got to explore a lot of the city. And it was great. I met a lot of great developers through that process. So fast forward a little bit more, 2009, 2010, I started getting more and more interested, involved in the Ruby community. In 2009, I was fortunate enough to receive the Ruby Hero Award for my contributions to Event Machine. And I started going on the conference circuits. So I was going to all sorts of conferences, giving lots of talks on threading, GC, memory profiling, debugging, so on and so forth. At the same time, GitHub really started taking off. All the best developers that I knew that I had met through all these drink-ups, they slowly were going to GitHub. And by 2011, enough of my friends were there that I was like, I want to work here as well. And so in 2011, in the beginning, February or so, I joined GitHub as well. That was my blog post. It's actually a funny story. I was actually consulting during that time because I had a lot of expertise in memory profiling. I was working on some REE patches. So I was consulting in places like Twitter, and GitHub was actually one of the places that I was consulting. And as soon as I got access to that code base, it sort of changed my life because I realized that this product that I had been using every single day, I could now actually go and make changes to. And so what happened was actually I started in my spare time adding this feature to the file finder. And I had it working, and then I was like, I want to ship this, you guys. And they were like, you don't work here. You need to work here first. And so on my first day, I actually shipped this feature as well, which is really cool. So moving on, so that's enough about me. Let's talk about Ruby at GitHub. So when I joined GitHub, GitHub is sort of a unique service in that it's much more than a Rails app. You know, in a traditional Rails app, you have sort of an Nginx Rails, and it just uses Ruby. But we have an entire Git stack that runs in parallel, and all of those pieces also use Ruby as well. And so, for instance, anytime you make a push to github.com, we run a post-receive hook that is written in Ruby. And all these things at the time were just using the system Ruby package, user bin Ruby, and it was 187p72 because that's what shipped with Debian. As one of the first things I did actually as a newcomer to this large production environment, I found myself over and over thinking, what is going on inside these processes, right? I would log into one of our servers and see a unicorn running or one of these hooks running, and I always wanted to look inside the process and understand what was happening. And so one of the very first tools I wrote in my first few weeks at GitHub was RBTrace. And this is one that we continue to use to this day. I would highly, highly recommend all of you checking it out. It provides a number of features that let you attach to a given Ruby process and get a lot of information out of it. So you can do stuff like inject a profiler, or get debugging information out, or change variables, or even watch for slow methods, for instance. There's a number of methods and functionality, and it's inspired by another tool I'll talk about later, strace. So even by 2011, actually, I think Ruby 187 P72 was highly out of date, and it was actually kind of embarrassing. People would ask me, what Ruby are you running? And I was like, P72? We had a couple of security patches in there, but it was highly dated. And so my first sort of goal at joining GitHub was like, I know about REE. I had spent the last year or so developing some patches for REE. I knew that it performed really well in production. It exposed a bunch of GC tuning variables that allowed you to get a lot of performance out of it, and also had linked tcmalloc, for instance, which out of the box provided a lot of benefits. But this ended up actually being a very tricky process. So I mentioned, there's all these different stacks that are all using Ruby. And what I wanted to do was just ship a new Ruby package up RE and install it. But it was sort of a scary thing to do, because what if the get receive hook all of a sudden breaks on this new version of Ruby? It was uncertain. And I didn't just want to install a new Ruby on all our machines and then have no clear way to roll back. Fortunately, GitHub has a really great testing culture. We have an incredible CI that has very, very good coverage. And so I leaned on the CI to try to get validation about this new Ruby build. But that in itself was also a frustrating process, because CI at that time was very slow. So it would take about 8 minutes to do a full build. And that was with some parallelization that had been built in. Without parallelization, it was about a 20 to 25-minute build. So my first step became, let's actually try to make the CI faster, so I'm not spending so much time just sitting around waiting. So I want to talk a little bit about how I think about performance and how I go about measuring performance. So the first step for improving performance is measurement, always measurement, right? If you can measure what is happening, only then can you try to make changes and then figure out if your measured times have increased or decreased. And instead of simply measuring how much time something takes, I always break down that time, execution time, into two major parts. So there's CPU time and idle time. So CPU time is time on your processor. There's an Intel processor in most of your servers. The time that's spent executing instructions on that processor. And this can happen either from the kernel, which you call system, so system calls, or it can happen from user land, where either C code or Ruby code is actually executing, again, like adding, subtracting, using instructions on the processor to perform work. The rest of the time is something known as idle time, and that's generally attributed to any time that's part of the execution but is not spent on the CPU. And this is generally I/O time. So for instance, if you're connecting to a MySQL server, a Redis server, making a query, and then waiting for the result to come back, nothing is happening on the CPU. The kernel is smart enough to just wait and sleep your process, but it still counts. It's still part of your latency. It's still part of your response time. So when we talk about system time, this is where one of my favorite Unix tools comes in, strace. This is a tool that I probably use every single day when I'm working. And what strace does is it shows you all the system calls that are happening in a process. So you can attach to any given process and see in real time the system calls that are happening. And system calls are essentially functions, just like you would have a C function or a Ruby function, but this is a function that's defined in the kernel. So when you jump from user land to kernel space and execute a function there, like read, write, connect, anything like that, that's what's known as a system call. So one of the first things I did was, OK, we have this CI build. Let's run strace against it. And strace has a number of modes. One of the modes is -C, which sort of gives you a summary at the end of where your time was spent. And what we noticed right away was 76 seconds was spent in the kernel on the clone system call. So the clone system call is what powers the fork concept in Unix. And so anytime you want to create a new process, you fork off a process, and it creates a complete copy of your process space of all your memory. And it uses a concept called copy on write, but it's still on Linux, ends up getting slower and slower as you have more memory. So if you have a 500 megabyte or a 1 gigabyte Ruby process, it'll actually take you up to half a millisecond or even a millisecond to perform that fork, because all the page table entries have to be copied. Not necessarily all 1 gigabytes, but the metadata that tells it where all the 1 gigabyte data is has to be copied to the new process. And so this was what was happening here in our CI. Especially, we invoke Git a lot. We depend on Git. And so every time you would invoke Git, since the Ruby process was so big, it was incurring a huge amount of latency. So one of my first projects, Ryan Tomeko and I worked on, was we discovered that most BSDs and Linux offer a different system call that's optimized for the case where you're executing a different process. So fork is generally used for two different things. One is to create a copy of your process and just leave it be, or you can fork and then exec another process. In the fork exec case, you don't necessarily need to copy all the memory because you're just going to be executing a different process. And so we discovered a system called POSIX Spawn, and we built a Ruby gem around it that emulated Ruby 1.9 Spawn API. And we put this into our CI build, and all of a sudden, our CI was twice as fast. So now that we had a faster CI, I could take a step back and go back to my original goal. So what I decided was it's too scary, too unreasonable to just roll out a new Ruby build, right? I don't want to break github.com for everybody. And so what I decided to do was install this new Ruby build in a separate directory. And so we started putting all our Ruby builds in user share RBN versions RE, as you can see. What this meant, though, was that in every one of the stacks, I had to go in and make sure that I told that stack to use the new Ruby build. And this involved going in and changing the path, setting the Ruby version, and then also, since RE offered a bunch of GC tuning, we put the GC tuning variables in there as well. So this worked out really well. It turned out there were actually no problems. I was being overly cautious. CI was green. Production was fine. And so within a couple of days, we were able to switch over completely from Ruby 1.8.7, no more P72. We were on RE, somewhat of a more modern Ruby. So next up was Ruby 1.9, right? With a successful strategy now for being able to do Ruby upgrades, we wanted to start thinking about Ruby 1.9. And we were, again, relatively late to the 1.9 game. By this time, 1.9.3 was already out. And this actually turned out to be a good thing because Ruby had matured a lot. The RVM had matured, and there were a lot of issues initially that had been resolved by the community. A lot of gems had gotten 1.9 support by this point. And so it actually became a lot easier for us to do this upgrade. The way we approached this upgrade was a dual boot system. And so we ensured that master branch of GitHub could run in both Ruby 1.8 and Ruby 1.9. This was fairly straightforward. A lot of these things, like I said, had been documented. There were several great blog posts by other startups that had performed this upgrade. And so we did, normal things like switching away from faster CSV and gems that were deprecated, syntax changes like the case syntax, changes to array and fixed num, no longer coursing to strings automatically, the new YAML parser, enumerator changes. And so we were progressing pretty well. One of the things that was a huge sticking point, though, was Marshall compatibility. So GitHub relies on a large memcache cluster. We have a memcache cluster that's several terabytes large, and we rely on a lot of our Git data being in cache, so we don't have to hit the file system over and over again. But with our dual boot Ruby, we started noticing anytime I would branch deploy into production, we were seeing Marshall and compatibility errors. And actually, the Ruby 1.9 processes were dirtying the cache, and then once you had polluted the cache, the 1.8 processes started blowing up as well. And so I started investigating this, and it turned out to be not that hard. The major incompatibility was in the date and datetime classes, and this was due to the underlying issue was a change in the rational class. Rational had become a pure C implementation instead of a pure Ruby implementation. And what I discovered was it was actually pretty easy to write a monkey patch for 1.8 and a monkey patch for 1.9 that added cross-compatibility. And so this is actually just, I meant to blog about this, but I never did. So if anyone ever needs to upgrade from 1.8 to 1.9, you can use this, and it works really well. And what this meant was now we could have some of our servers on 1.8, some of our servers on 1.9, both of them in production, both sharing one huge memcache pool, and we could just keep switching back and forth. And The process at this point was, I would deploy 1.9 for a couple minutes, a couple hours, go look at our exception logger, find all the exceptions, try to fix them, so on and so forth. So this worked really well for a while. And then the largest remaining issue was encodings. So lots and lots of encoding errors. Everybody was opening encoding issues, lots of help support cases for people having issues. And so the solution here was a huge hack on my part. What I did was I patched YARV to be more like 1.8. So the first step was we collected a lot of test cases. So we collected tons and tons of test cases. And the hard part in our case is that people are uploading Git data, right? Git has a lot of data. Author names, email addresses, commit messages, all sorts of stuff, even tag names, branch names, file contents. All of these can be written in any encoding, depending on if you have a Windows machine or whatever your operating system decides what the encoding is. And unfortunately, Git itself never records the source encoding of what's being committed. And so what happened in our case is we go to Git, pull out a commit message, or pull out even a file name, and it turns out we think it's in UTF-8, but it's not. And we have no idea what it's encoding it's in. And so when we try to combine that with a non-UTF-8, or combine a non-UTF-8 string with a UTF-8 string, it would just blow up completely. So our solution here was, like I said, a huge hack. And what I did was I added an option to the VM called encoding compatibility. And I've never actually talked about this because I'm a little embarrassed that we had to do this, but it actually ends up working pretty well for our case. And what happens here is basically when you're now joining an ASCII 8-bit string and a UTF-8 string, instead of raising an exception, we swallow the exception and ensure that the resulting string is tagged as ASCII 8-bit. And so anytime you do an operation that takes a binary string and any other string, you end up with a binary string. And so it more closely emulates Ruby 1.8's behavior. So this got us past the last major blocker. And the last thing we wanted to do, so if you remember my earlier slide, the way that we were rolling out Ruby upgrades was going into the Git stack, going into the Rails stack, and updating these environment variables. And this was very cumbersome. I didn't want to go onto every server or every single stack and keep changing environment variables back and forth. So the solution we came up with was this concept of bin app Ruby. And so this is a very simple shell script that we generate during deploys, and we hard code the paths to the Ruby that we want to use into that shell script. And you can see as well we add the encoding compatibility flag, as well as any GC tuning variables into that. So the way this works is we tell bundler, it has a few options, the bin stubs option and the shebang option. We tell it basically for all the bin stubs that it's creating to hard code the app Ruby as the shebang. And what this means is if you look at the generated bin stub, for instance, for Unicorn, it has at the very top, tells it to use bin Ruby, bin app Ruby. And so all we need to do to switch from Ruby 1.8 to 1.9 is edit app Ruby and have it use 1.9. And this actually ended up working really well for us because it automatically handled Ruby upgrades during deploys. And so when you deploy Unicorn, for instance, the way it works is there's Unicorn master, and it forks off a new Unicorn master, and it does that by invoking bin Unicorn. And if bin Unicorn is pointed to app Ruby, it'll automatically use Ruby 1.8 or Ruby 1.9. And so this meant that we could just go into chat, tell Hubot, deploy my Ruby 1.9 branch, and all of a sudden, all the Unicorn processes rolled over and started using 1.9. If you needed to switch back, you just do a deploy, and it would switch back. So this was a huge win, and we used this process again, keep deploying back and forth, making sure master could do both, narrowing down the number of exceptions that were coming through, and then finally, we just shipped 1.9 completely. So I merged my branch, and we saw a huge decrease in CPU time. Again, this is not necessarily average response time total, but average CPU time. So we're not counting any time waiting for MySQL or Redis. This is literally time spent on the CPU, and you can see we went from almost 100 milliseconds to about 60 milliseconds. So this was a huge win for us. And we saw much bigger wins actually on 98th and 99th percentile, up to 40% improvement in mean, but 99th percentile was almost 60% improvement. So now we were finally on YARV. This is a very exciting time for us. We had ditched all our legacy 1.8 stuff, and now we had a much better base to work on performance from. So I decided now to make performance my #1 goal, and I started writing a lot of tools to get better visibility into where the performance times were going. And so one of the first tools I wrote was a very simple script called bench app. And what this did was literally create a mock request in a loop and kept hitting our Rails app. So for instance, here's an output. Hopefully you guys can read this in the back. It's making on the top left 50 requests. You could give it a URL. So in this case, this is a large pull request. I think this is actually the Ruby 1.9 pull request itself. I'm hitting as myself. And so you can see you get a lot of information. And at the top here, the circled red is, again, we have this concept of CPU time and idle time. And you can see on this page, it's actually very CPU heavy. It's taking almost 820 milliseconds per request on the CPU crunching data. And this was because this was a very large pull request with thousands and thousands of commits by this point, by the time it got merged. On the idle time, you can see we're spending about 200 milliseconds. And so again, this is time that's spent just waiting, and it's waiting on either MySQL, Redis, Memcache, or Git access. And then finally, you'll notice as well, I've added a bunch of allocation and GC stats in here as well. And this was our primary method of doing GC tuning. We would run benchmarks like these and try to get a sense of how many allocations and how much time was being spent in GC. So again, for this really large pull request, you can see it's making almost 1 million object allocations per request. And whenever GC happens, it takes 300 milliseconds. So this was obviously on Ruby 1.8. Ruby 1.9 is much faster on GC. But this was a very useful tool for us to get a sense of, for any given page, where is time being spent. Is it on the CPU? Is it waiting on network access? Is it being spent on GC? Are we creating a lot of objects? So on and so forth. Another tool I started writing at this point, so I actually have this, I've developed this fun hobby over the years. I really, really like writing profilers. I don't know what it's about profiling, but it's this idea of being able to look inside your Ruby code and really see what it's doing. I really enjoy it. And so over the years, I've written a lot of profilers. Back when I was working on 1.8 and REE, I wrote perftools.rb, which worked pretty well, but it was very hacked together. And when I tried using it on 1.9, most of the times it would just segfault. And so I decided to write a profiler that was focused on line-by-line annotation, because we noticed in our large application, it was very hard to get a sense of where time was being spent in templates, in controllers. You would maybe get a method, but you didn't necessarily know if, for instance, an ERB template is just one giant method. It might be a 1,000-line ERB template. It's just one method. And it'd be really nice to know line 26 of this method is where it's slow. So RBLineProf works really well. It works with 1.8, 1.9, REE, 2.0, 2.1, everything. And the way it works is basically it gives you a line-by-line annotation. So here, for instance, is the dashboard page. I noticed one day I just started profiling random pages, and I noticed that there were these logging debug things that someone had just left in. And so on every single dashboard page, when you hit your GitHub homepage, we were spending about 14 milliseconds just printing out something to logs that no one actually looked at. And so this was very easy. I just got rid of those lines. Big win. And so we kept doing this over and over again. We found a lot of easy wins all over the place. And so now I started getting deeper and deeper into Ruby, and one of the things I felt lacking was there was not a lot of collaboration going on. And I wanted to reach out to more people using 1.9 and understand how they were dealing with performance issues. And so we created this campfire room on our GitHub organization called Ruby Performance and invited a bunch of people to it. So Charlie Sum, Tenderlove, Funny Falcon, James Golick, Sam Safran, and a lot of very interesting work happened in here. Actually, James Golick's method caching patches that landed in 2.0 and 2.1 were actually developed as part of this chat room as well. And then one day, James Golick asked me in the chat room, hey, Aman, why don't you have commit access to Ruby? You're working on all these patches. You should have commit. And I said, that's a good question. Maybe I can ask Matthew for commit access. So I request commit access. And to my surprise, he actually agreed. And I became a Ruby core committer. That was a very exciting day for me. So now that I had commit access, I felt very much empowered to develop a lot of the tools that I had wanted to see in Ruby. And again, pursue my favorite hobby, writing profilers. And so Sam Safran reached out to Koichi-san and created this Ruby Profiler Task Force Skype room. And we spent a large majority of 2012 in the chat room developing the sets of APIs that ended up shipping with 2.1. So these fell in two major categories. One is profiling and tracing, and the other is GC. So on the profiling side, what I wanted was to write another sampling profiler. So RB-lineprof is not a sampling profiler, it's more of an exact profiler, and so it has a lot of overhead because it instruments every single method call. The nice thing about perftools.rb and a sampling profiler is that you can control, as a developer, as a user, you can tell it how much overhead you want, how often you want to take samples. And so it's something that you can actually run in production with very little overhead, 1 to 5% depending on how often you tell it to sample, overhead, 1 to 5% overhead at most. And so to do this, we needed an API that was built into Ruby that would let you, from C level, grab the Ruby backtrace. So the way a sampling profiler works is you tell the kernel, every 1 millisecond, take a sample. And the sample is the entire Ruby backtrace. And once you collect hundreds of these samples, you can start to aggregate them and see, oh, most of these samples were in this one method call, this other method call, so on. And I wanted to be able to do this without any CPU overhead, but also without any allocation overhead. In Rubyland, when you call backtrace, it generates a bunch of objects. And so that's not ideal if every 1 millisecond you're taking a backtrace and you're generating a bunch of garbage objects. It's going to have too much overhead. And so we designed this API, RB Profile Frames, that is available from any C extension and lets you, with 0 allocation overhead and very minimal CPU overhead, grab a Ruby backtrace. On the GC side, we added memory debugging. So back in the day on REE, Joe D'Amato and I wrote this tool called memprof, which was very similar, that basically let you do memory introspection and memory debugging in a Ruby process. And so again, I went to Koichi-san and we discussed a variety of APIs to figure out how to expose this information to C extension developers so that they could get events every time an object is created, get an event every time an object is removed. And then on top of those trace points, we were able to build a lot of cool functionality, for instance, the allocation tracer. The way it works is every time an object is allocated, it gets the event, and it can record, again, either the backtrace or the method call where that object is created. And now, all of a sudden, you have this plethora of information that you can, again, aggregate and figure out that, oh, this method is creating way more objects than this other method. And finally, we added a heap dumping API. So again, this was a part of the original memprof design. And I'll talk about this a little bit later as well. So with all this, all these patches and new APIs landing in 2.1, again, at this point, I had commit access to the trunk, and I was working with Koichi-san. We committed a lot of these back. I was very excited to get this into production. And so what we ended up doing was forking 2.1, and we have a very minimal set of patches on top, mostly the encoding compatibility patches. Funny Falcon had developed a method cache patch that we were using in production that I'm hoping might land in 2.2. And then some small backports. One of the other things we started to do as part of this process is generate, these are 2 make commands that you can use whenever, if you're ever building your own Ruby. And as part of the Ruby package that is shipped to all our servers, we actually include 3 Ruby binaries. So one is the regular Ruby, but then we also include a Ruby jemalloc and a Ruby tcmalloc. And what this means is any application can choose what allocator it wants to use. And for our use case, we actually found there's different trade-offs in the different allocators. So on some servers, we use jemalloc, and on other servers, we use tcmalloc, just depending on the trade-offs that we want to achieve. So this works really well. With this new Ruby package ready to go, it was time to start putting it into production. So again, this ended up actually being pretty simple because it was mostly compatible with 1.9. So we did a branch deploy. It was looking fine. I let it run over the weekend. Got back Monday morning, hit merge. And as you can see, CPU time decreased a little bit, sorry. Got a little bit better. And the big dramatic change, of course, was GC. After Koichi-san's work on RGen GC, we saw a dramatic improvement in GC times. So you can see on the top graph it's a little bit hard to read, but if you look at the green line, that is the median GC time spent in production. And so before the upgrade, median GC time was close to 100 milliseconds, and afterwards was down to 15 milliseconds, which is amazing. And then on the bottom, you can see the total GC time. You can see we're doing much less GC overall. So whenever somebody hits github.com, there's not as much time being spent in the garbage collector. Response times are much faster as a result. So the numbers were looking great, like I said. So we hit merge, and now we were running 2.1 in production. And now that I finally had Ruby 2.1 in production with all these new APIs, it was time to take advantage of these new APIs. And so I went off and I started developing tools that use these new APIs. The first one was StackProf. So this was my dream, again, of a profiler, a sampling profiler. I wrote this. It actually ended up being very simple. It's only 300 lines of code in a C extension. Most of the heavy work is done by the new API that was introduced. I wrote a very extensive blog post about this on my website, so I'd recommend checking that out. But I'll go through some examples. So again, one of the nice things about StackProf is that given the amount of data it can collect, it can generate a lot of different types of reports. So one of the reports that it generates is very similar to RBLineProf, but again, this is done in a statistical manner, so it's much less overhead. And so here's an example. For instance, I noticed that 31 milliseconds on any issue page in the assignee dropdown was spent just rendering this in this radio button helper in Rails. And so I just converted it to static HTML. Got a bunch of time back. One of the other reporting outputs that StackProf can generate is a graph. So what's happening here is this is a call graph, right? Well, every time you grab a stack trace, you know exactly all the methods that were called from the beginning, the main function down, or up rather, to the top stack frame. And so we can generate this graph based on all that stuff and get a very clear sense of where time is being spent. So this might be a little hard to see, but on the top there, that is the compiled ERB template for diff lines. And so that, what I did again here was, like I mentioned, you can run this in production. So I actually enabled StackProf on one unicorn in production for a number of hours and just let it sit there, collect a bunch of data. And so overall, over that 2-hour period or so, almost 15% of the time was spent in this one partial, just rendering diffs. And so if you start following the arrows down, you'll see that in this diff lines partial, there are two major things happening. So diff lines is about 13.9%. And then on the left here, there were a lot of calls to parameterize. That was about 5% of the times. 5% of, again, we're talking CPU time on the processor is being spent just in that method. On the other side is a string to MD5. So again, that's about 1.3%. So not as much, but we were doing a lot of MD5 generation. So armed with this knowledge, again, looking at this right away, okay, now I know parameterize is getting called a lot. When you go look at the code, it becomes very easy to spot what things are happening. And so you can see the circle line over there, there's a loop. And inside the loop, we're calling path.parameterize. So for each line in the diff, we're calling parameterize on the path, and the path is the same. It's the same file over and over again. So we're just calling it over and over again. And it's a very simple optimization, loop optimization. Pull the variable out of the loop. Boom. That's, 4.5% win right back there. So as you can see, you have there's a lot more examples like this, but getting that visualization, getting that insight into what is happening in the Ruby process makes it that much easier to then go and make improvements to your Ruby code. The final output method in StackProf is flame graphs, and this is really cool. So this is what a flame graph looks like, and it basically is a timeline. So on the left is the beginning of a request, on the right is the end of a request, and you can see these are, every one of the spikes up is a sample that was taken. And so going up from the bottom, that's a full stack trace. And it's colored so you can sort of see different gems. So the yellow, for instance, is action controller. So everywhere you see action yellow, that is calling into a method inside action controller. One of the cool things in here is that, let me see if I can play this. This is an animated GIF, but it's not playing. Oh, there you go. So there's this D3 UI that comes with StackProf, and you can start to see on the right are all the gems that were pulled in, and again, it's all color-coded. And then you can actually start to zoom in and take a look at exactly all the methods that are called and how long they're taking. So for instance, over there in the dark purple is the I18N library, and again, on the bottom, you can see the full timeline, so you can actually start to drag and zoom into the area that you care about and really get a sense of where your time is being spent. So this is a fantastic utility, and we've started using this a lot more. So recently, we upgraded from Rails 2 to Rails 3. Rob Sandheim talked about this a few days ago. And as soon as we started branch deploying that, we noticed a lot of performance regressions. And so we were able to jump into StackProf, look at the various flame graphs, and we noticed that on the left, you see after the router, we just jumped to the authentication method right away. But on Rails 3, there was a huge time span in the middle where we were spending a lot more time inside action controller doing all sorts of stuff. And so once we knew, again, that method for action was the hotspot, we could then go into our Rails 3 fork, figure out the problem, optimize it, and get rid of it. And we eventually did, and then we were able to ship Rails 3 and maintain the same performance profile that we had with Rails 2. So like I said, these are just a couple of examples. There's a lot more. We've used StackProf, LineProf dozens and dozens of times all over our infrastructure to find hotspots and improve them. Lots of people in the community have started using it as well, and I encourage you to try this out on your application. You'll be amazed at the amount of insight you can get into your Ruby code. And if you do end up finding something interesting, tweet at me and let me know. It's always exciting to hear about what sort of slow things people are finding. And then alongside the new profiling APIs, like I mentioned earlier, we introduced a set of memory debugging APIs. So this was always a pet peeve of mine, even going back to Rails, to RE in 1.8. When I was working on large applications, it was very easy to get memory bloat, and there were no utilities to understand where that memory was going. With 1.9, it got a lot better. With 2.1, we actually shipped a full-on heap dump that will let you do memory analysis. So a simple example for this from a couple months ago, I discovered I was taking some heap dumps off of production, just looking through them, doing some analysis, writing simple Ruby scripts that did aggregation. And what I noticed was I saw a lot of strings that were 4 kilobytes in size. So what's happening here is on the top you see every time you call file expand path, I'm dumping it out. So the way the object dumping works is it creates a JSON object for each Ruby object that includes details about that Ruby object. And what you'll notice here is the byte size is only 4 bytes, right? That's /foo, 4 characters, 4 bytes. But the capacity and the mem size of that object is 4 kilobytes. And what was happening here was the way file expand path was working, it was allocating a large 4 kilobyte string up front because that's the maximum possible size for a file path. And then it would never shrink this string back. So I opened a bug report about this. Nobusan fixed it in a matter of minutes. And we deployed it to production. And we noticed right away we saved 22 megabytes on every single Rails process just because we had so many of these path strings all over the place. One of the ways I verified this change was, again, using a C-level profiler. So again, the tools that we're shipping with Ruby now give you a Ruby-level sense of where memory is going. But sometimes, like in this case, the leak is actually on the VM. And so one of the tools I recommend for that case is jemalloc. If you're using your Ruby linked against jemalloc, it includes a statistical profiler built in that you can enable. And so again, here it gives you a very similar sort of output, and you could see the file expand path 1 helper method inside the VM was where we had allocated almost 30 megabytes. And again, with this patch, we were able to reclaim 22 megabytes of that back. So next up was, earlier I talked about how for the 1.9 upgrade, what we ended up doing was introducing this concept of app Ruby, and it would point to these user share RBN. As we started, so by this point, Charlie Sum had also joined GitHub, and the both of us were iterating on a number of Ruby patches very quickly. And so it became very cumbersome to every time we wanted to try a Ruby patch, you had to go and create a Debian package, go install it on the machines, and then go and change app Ruby. And so what we decided was it would be much simpler just to vendor it. And so what happens now in our workflow is actually every time you deploy Ruby, deploy github.com, it will build a Ruby inside vendor Ruby and then point app Ruby to that vendored Ruby process. And so this actually works really well for us in that when I wanted to deploy this expand path fix, it was just a matter of going in and changing the Ruby version SHA and then deploying it. I could branch deploy it, and it would notice that the SHA had changed, build a new Ruby, update app Ruby to use it, and then all of a sudden your new unicorn is now on the new Ruby. And if it doesn't work, you can easily switch back, tell Hubot to deploy master, it switches back. So this workflow worked really well for us. And then finally, I wanted to go through a few more tools that we've developed. And these are tools that we have built right into our application. And so as a developer of GitHub, or rather as an employee of GitHub, we have this bar at the top of GitHub that we know called the staff bar. And we include a lot of interesting performance data about the current request in there. So this, there's an open source version of this as well that we have open source called Peak. So if you haven't checked this out, I recommend installing it in your app. And it allows a similar facility to be able to go in and tell it to only enable it for authenticated requests. So it will only be enabled for admins. But the cool thing here is, so on the left, for instance, you can see This request took 471 milliseconds on the server side. And again, we break that out into CPU time and idle time. So CPU time was the majority at 430 milliseconds, and the remaining was idle, waiting on, for instance, 37 in SQL, 4 milliseconds in cache, 1 millisecond in Redis, so on and so forth. You also get to see that one garbage collection happened during this request, taking 164 milliseconds. So just very quickly on any page, you can get a sense of where is the time being spent. And the really nice thing about this is you can click on any of these and get more details out. And so, if, for instance, if you click on the template rendering, you actually see all of the ERB templates that were rendered for the request and how long they took. So here's one of our developers noticed that the recently touched branches, whenever you're looking at tree view on GitHub, was using the majority of the time. And again, this gives you this level of visibility into the application that empowers you to go in and start making improvements. If you just know that the page loaded in half a second, you can't really do anything about it. But if you know that this specific template spent 38% of the time, then you can go start looking at the code for that template, start profiling it, start running a line prof, and figure out exactly what line needs to be improved. Next is the MySQL. So again, if you click on that MySQL link up there, you get to see every single query, how long it took with the entire backtrace of that query, and also the server that it ran against. So again, a lot more information, a lot more detail about what's happening. This is another one of the tools that we actually don't use this in production yet, but I have a branch that I worked on over the weekend a couple months ago. And the idea here is template visualization. So this, again, is a movie, if I can get it working. Basically, you can hover over, there it goes. You can hover over any element on the page, and we actually annotate the output HTML to tell it not only what template, but how much time it took. And so this is, again, a very easy way to tell what parts of the pages are hot. And we could do a lot of cool stuff with this. You could do sort of a heap map, for instance, and say that this specific part of the page is taking up a lot of time to render, and so on. So that's pretty much all I have. To recap, Ruby 2.1 is definitely production ready. We love it. We're running in production every day. The new profiling and object space APIs make debugging easier and actually a lot of fun because you get to see what is happening in your Ruby process and improve your Ruby code with direct feedback. And really, this is the only way to improve your Ruby performance and to get a better sense of what Ruby best practices are. Even from the quiz show earlier, for those of you who were in here, it's very hard to compare two pieces of Ruby code and without context know that one of them is faster and one of them is not. It depends on the implementation. And so the more you can do to get data out about what the VM is doing, the less of a black box it is, and more of these tools that we have available to us, the more empowered we are to improve the performance of our ecosystem as a whole. So that's all I have. I'm happy to take any questions.
Thank you for your great presentation. We have some minutes, so if you have any questions, some minutes Q&A. じゃあ誰かいた。
Thank you for a great keynote and your great contribution. Thank you very much.
Thank you very much.
Mike. My question is, just now, what do you want to improve about Ruby interpreter itself?
That's a good question. I'm actually very happy with the way things are going right now. I think for me, I want to add more. I think we've talked about this as well. I want to add more tracing APIs that can be not global. So the only way to trace methods right now is to install a global trap handler and get a call and return event for every single method called. And what I would love to be able to see is to be able to go to a specific class or a specific method and get only events about that class. And that goes back to RBTrace. The way RBTrace is implemented right now, it adds a lot of overhead. But if, for instance, it was possible to go into a process and say, show me every single method that's called on action controller, I think that would be a huge win because you would be able to do very scoped debug information out about specific classes, specific methods, and add timing around those specifically.
Okay, thank you.
Yeah, my question is related to profiling. How do you figure out random slowness? Like one endpoint that usually responds is 200 milliseconds, but all of a sudden there's one request and make it like respond in 20 seconds. You know?
Oh, just sometimes it's slow.
Sometimes it's
yeah,
just
that's really
sometimes.
hard. It's hard to tell, and that's why my inclination is always to run these sort of profilers in production, because a lot of times it's very hard to, in a synthetic environment, try to replicate the same types of issues you're seeing, especially a lot of those types of issues that end up being network related, or if your MySQL server is overloaded, you might start to see those types of problems. And so my goal has always been to enable these tools to be low cost enough that you can actually run them in production. And that's really the only way to do it. If you can go and enable a profiler for one whole day, then you have enough data at the end of that day to go in and deep dive and figure out why was things slow. And especially if the data includes CPU versus idle, then it's very easy to say that, oh, it's a code problem or it's a backend services problem.
Okay. Next. いらっしゃいませんか？あ、田島さん。
Hi, my question is online profiling versus offline profiling. So, are these tools are all online profiling or offline? And if it's offline profiling, then do you want to any kind of online profiling which you enables always on the production environment?
So these are meant to be able to run in production. The way we use line profiler is much more overhead. And so the way that one works, actually in that staff bar, we have a button. So you hit the button and it gives you a profile for that page. So that's the way we use that one most of the time. With StackProf, it's meant to be low overhead, and so you can run it in production. And you can, again, the way we do that is since we have so many servers, so many unicorns, we will usually take one server and enable profiling on it and gather data over multiple hours or multiple days.
Thank you very much.
じゃあ次 next question is last. あ、じゃあ、上まで上がって。
When can I have your visual profiler that you showed there at the end?
The template profiler?
The template profiler.
It's a huge monkey patch on Rails that I could post it up in a gist. We actually haven't shipped it yet because it's very hacky, but it is kind of cool. So I'm happy to tweet you a link to it.
Thank you so much.
All right, thank you, everybody. If you have any more questions, feel free to find me or tweet at me, send me an email. I'm happy to help. Thank you.
Okay, thank you. Thank you.